So today we will find out what kind of shape this is. This is a catenoid, and it has the property that it's a minimal surface. Okay, so first of all, let's assume a few things. Okay, so these are the four things we need to assume. First of all, we have no gravity. As you saw in the soap thing, it changes if there is gravity, so we will just not assume it. Second of all, as I said, this is a minimal surface. That's a thing we will assume. Third of all, that's a strong claim. We say that around these axes, like the middle axis, f of x is a body of revolution, which just means I can turn it, like I can turn this function around this axis, and then after that I will have the surface, right? The object, right? So as I described, this is f of x, and we will also assume that f of x is 2 times differentiable. So first of all, let's just see how we can describe the surface of the catenoid. We will write this as a surface of catenoid. And this is equal. So let's see. First of all, we have what is 1 times the perimeter. So this is just a circle, so it's 2 pi times the value of f evaluated x. So secondly, because this won't yield us a continuous function and not the whole area, so what we need to look at is just a really small part where we include the slope and everything. And this is actually just the formula of the arc length, as you saw in the last video. So you might remember this is just 1 plus f prime of x and then square of that. So, and of course, because we have infinitely many parts of these packed in this area, we will just integrate this. So now because we want to minimate something, there is a formula for this, but I can't derive it sadly. I'll just show you. So first of all, we have to define the Lagrainan. It's in terms of f of x and depends on f prime of x. I know this sounds weird, but it's just the way it is. So this is just everything that's answered under the integral sign. So in order to minimize this, normally what you would do with normal variables is just set it equal to, take the derivative and then set that equal to 0. We do something similar here, but we are not dealing with variables, but with functions. We want to find the best function, not the best variable. So that's the whole function. It's called the Lagrainan Euler equation, I think. And it just means we take the partial derivative of L in respect to f of x, and then we take the partial derivative of L in terms of f prime of x, and then we take d over dx. So it's not too difficult, but we need to do all of this. So because we need to write a lot, let's just change all of the f of x's to a y. So let's begin evaluating this. So first of all, let's take the partial derivative in respect to y. This will be equal to, well, there's only one y here, and the rest is a constant. So we can just forget all of the other stuff, and this will just be that exactly. So that's not too difficult. So now let's find out the partial derivative in terms of y prime. And that's a bit more tricky because, well, first of all, this is all a constant, so we can write all of this out. And now we need to differentiate that, so it's also not too hard. Use the chain rule. This is 1 over 2 times the square root. The inside stays the same, so we can just use this. Now we need to redifferentiate that. So this is times 2 times y prime. And don't think that we need to differentiate y prime here as well, because that would be dx, but this is the variable. So that's right. And now let's take d over dx of all of this. So that's a bit more tricky. First of all, we can see that these two things cancel. Sorry, I didn't do that earlier. But we will just pull out all of the stuff on the top and then multiply it by everything that's here, like this fraction. So here we will just use this as a u, this all will be u, and this all will be v, and we can just use now the product rule. So let's do that really quick. First of all, let's differentiate the first u, so this is 2 pi, and then we use the product rule again, so this is y times y prime plus 2 pi y prime and then squared. Right, so the rest stays the same, so this is 1 over square root of 1 plus y squared. Just write it as this. Then we add, this stays the same now, so this is y prime, and then we differentiate all of this. So keep in mind this is just the bottom to the power of negative 1/2, so we can just pull out the exponent, so that's negative 1/2. And then we differentiate that, so we subtract 1 to the exponent, so this is 1 plus y prime squared, and then we raise to the negative 3 over 2. And of course we have to redifferentiate the inside, this is times 2y prime, and then because we differentiate in terms of x, we need to multiply y prime prime. Okay, and because this is really hard to deal with, let's just pull the complete function down here. So we will also do this. By the way, we can rearrange this. And this will now be equal to negative this. So this is negative 2 pi square root of 1 plus y prime squared. Okay, so we didn't change anything about this, so this stays plus. Now first of all we can cancel this 1/2 and this 2, and we can, since this is just equal to 0, right? We set that is equal to 0, so we can just multiply anything out we want. So we don't want this square root of this 2 pi anywhere. So this is all of the 2 pi is gone, and we will also multiply by this square root. So let's rewrite this. We multiply everybody by exactly this square root. So this will be equal to negative 1 plus y prime squared, since this square root squared is just right. So then we add what's inside is left is y prime prime plus y prime squared, and this just gets erased completely. And then we add, we subtract, because here's a negative, right? So we subtract, we subtract y prime, and then we also have y prime again here, so we have this. And then all of this times 1/2, that's just still 1 over 1 plus y. Exactly. Okay, so this is already pretty neat, but now we can do another thing. We can pull out this factor in all of the rest. So this is y double prime. And now we have, this is just 1. And then we subtract what's left here. Here's y prime, all of this. And of course, this stays over 1 plus y prime squared. But now we can do another thing, and we can change this 1 to a 1 plus y prime squared over 1 plus y prime squared. Sorry, that's so messy. But anyways, we see that these two now cancel because the numerator is the same. And this gives us negative 1 plus y prime, y double prime, all over 1 plus y prime squared. And because this is equal to 0, let's just add 1 and multiply by this, so we get y double prime is equal to 1 plus y prime. We can get back the parentheses squared. And that's a really neat formula. So if you already know the solution, you can now check this, but of course we don't. So let's solve this. So how do we solve a differential equation of like this? So we said, let's just introduce a variable p, and this will be equal to y prime. So this is just equal to dy over dx. And now we want to find out what y double prime is, and this is of course dp over dx, which is just equal to, we can introduce a new variable dp over dy times dy over dx. And of course this is just equal to p, so we get dp over dy times p. This y stays the same. We now rewrite this formula. We just figured out that this is dp over dy times p, and this will be equal to 1 plus p squared. Okay, so my battery ran low, but now we'll continue. So we get 1 plus p squared to the other side. So this is p over 1 plus p squared dp, and we get 1 over y and dy to the other side. So this is 1 over y dy. Okay, of course we can just integrate both sides now, and this will just be equal to the ln of y. And here, what we'll do, we set let u equal to 1 plus p squared, and then we get du is equal to 2p dp, and that's pretty good because we can just get a 2 here, and well, now let's substitute all of this in. So we get the integral of well, that's just 1 over u now, so that's 1/2 times 1 over u du. So this is 1/2 times the ln of u, and now we just plug in back what we have, so this times ln in absolute value 1 plus p squared. Okay, so because that's positive and this plus 1, we can just use a non-absolute value. So we get this, these two values are equal, so let's write this down. Okay, so we'll multiply both sides by 1/2, so we get 2 times the ln of the absolute value of y is equal to the ln of p squared plus 1. But now because that's a 2 and we have an ln here, we can just put it at the exponent, so we get ln, and now we don't need the absolute value anymore, so that's ln y squared is equal to ln of p squared plus 1. Now we can just e to the power of both sides, and that way we get y squared equals p squared plus 1. And now we plug in back the definition and subtract 1, so we get dy over dx squared is equal to y squared minus 1. Now we square root both sides, so this is dy over dx is equal to the square root of y squared minus 1. And now we separate the variables again, so we get 1 over the square root of y squared minus 1 dy equals dx. So of course now we integrate both sides again. So let's do that real quick. Of course this is just x. And the right hand side, well, how do we solve that? We'll set y equal to tangent, because let's see, we get, we know that secant squared is equal to tangent squared plus 1, so we get secant squared minus 1 is equal to tangent squared, so we will set that equal to secant squared. So let this is equal to x, so let u equal, let secant u equal y. Now we get that dy is equal to tangent secant of u du, and So the new integral is just tangent secant over, this is y squared, so that's secant squared minus 1, so that's tan squared, that's square root of tan squared, that's just tan, and all of this du, and of course tan and tan cancel, so we just get the integral of secant of u du. Now you might know how to solve this, but I'm just gonna do it real quick. So we multiply numerator and denominator by secant plus tangent. Excuse me that I'm forgetting all of the u's, but they are useless. Oh, yeah. Okay, so we get, now let's do another substitution. We said w is equal to secant u plus tangent u. And that means that dw will be equal to, so secant u is just secant tangent, and tangent is just secant squared, and all of this du. But that's just all of the stuff we got up here. So the new integral will be equal to 1 over w dw, which is just equal to ln absolute value of w. And w is secant plus tangent, so this is equal to ln of secant u plus tangent u. And of course now we have, this is equal to y, we know that, but we want to figure out what tangent u is equal to. So let's do a triangle real quick. We know that secant u is equal to y, so this means this over this is equal to y. So this might be something like this. And the opposite is now y squared minus 1. And tangent just gives us opposite over adjacent, so this is y squared minus 1. So we get this is equal to ln of y plus square root of y squared minus 1. And of course this is still, okay, and I forgot the absolute value because we had something like this function, and because of the domain and stuff, I can't explain it rigorously, but it's okay. And of course this is equal to x. So now we want to solve y in terms of x. Okay, so to solve this, let's just e to the power of both sides. And then we have y plus square root of y squared minus 1. And here's a neat trick, you can square both sides. And now we get y squared plus 2y square root of y squared minus 1 plus y squared minus 1. And now we can just, because this is equal to 2x, now we get 2y squared plus 2y. And now remember that this was equal to e to the x. So because here's the square root, we can just write this as e to the x minus y. And then we still have minus 1. This is equal to e to the 2x. And because this is 2 to the power of 2 times y to the power of 2, this and that cancel. So we get 2y e to the x minus 1 is equal to e to the 2x. Add 1. And now we divide both sides by e to the x. So this is equal to e to the 2x plus 1 divided by e to the x. We're almost there. Because we can rewrite this as, let's see, y squared is equal to, we can divide this. So this is e to the x, and this is e to the negative x plus e to the negative x. And that means that y is equal to e to the x plus e to the negative x all over 2, which is just equal to the hyperbolic cosine of x. And that's it. So now we know that the function describing a catenoid is, this is equal to cos, which is amazing. And it wasn't too difficult proving this. So, yeah. Thank you for watching. Don't forget to subscribe. Comment down below what you want to see next. And bye.